Hello everyone, welcome to my channel, and today's lecture is a very important lecture on statistics, testing of hypothesis. A statistical hypothesis test is a method of making statistical decisions using experimental data. Actually, you have some experimental data and you have to conclude something, statistical decision making. Roughly speaking, a result is called statistically significant if it is unlikely to have occurred by chance. In this chapter, we consider different statistical hypotheses and test them to make useful decisions on the basis of the experimental data. So before we deep into the depth of the things, it would be better to know what is actually meant of statistical hypothesis. So statistical hypothesis actually any short of the distribution functions fx, assumption of any short or about the distribution function of the population fx. So let E be a random experiment and S be the corresponding event space. Let x be a random variable defined on S and fx be its distribution function. Then any statement regarding the distribution function fx of the population of x is called a statistical hypothesis or simply a hypothesis. So that means any assumption of any short about the distribution function of the population, where the validity of the statement is to be judged on the basis of random sample drawn from the population of X. So you have to judge the validity. We assume that if X has a known functional form which involves a number of unknown parameters, theta 1, theta 2, theta, etc., theta k. So these are the unknown parameters in the known functional form. At present, this assumption will not be regarded as a statistical hypothesis. A hypothesis that consists in any assumption regarding the parameter. More than one population may also be concerned with a statistical hypothesis. Okay? So basically, what is statistical hypothesis? If I want to brief that thing, a statistical hypothesis is in general defined to be an assumption of any sort about the distribution of the population. So a statement, so here you have a definition, a statement regarding the unknown parameters of one or more population is called a statistical hypothesis, where the validity of the statement is to be judged on the basis of a random sample drawn from the corresponding univariate or multivariate population. So you have to judge this on the basis of random sample drawn from the corresponding univariate or multivariate. It can be multivariate population also. So let us consider a univariate population where the population random variable x has a normal m sigma distribution, m and sigma being unknown. Then the statements h1 such that m equal to 3, sigma equal to 4. H2 is another statement which gives m lies between 2 to 3 and sigma equal to 3, etc. are statistical hypotheses. So in here, you have to write the statement in the form of H1, H2, H0, such that maybe m is specified, sigma is specified, maybe m is not specified, sigma is not specified. So in this form, these are the examples. These are the examples of statistical hypothesis. Okay? So that is the definition and some examples. What is the statements of statistical hypothesis? Now, I will define another concept or give you the concept of parametric space. Let theta 1, theta 2, etc., theta k be the unknown parameters of a univariate population. These are all unknown parameters. The ordered k tuple of real numbers theta 1, theta 2, etc., theta k represents a point in the k dimensional space pk. You have a k dimensional space pk. So pk is a k dimensional space, and theta 1, theta 2, theta k is a k tuple of real numbers parameters. These are all unknown parameters called the parametric space. That is, pk is called the parametric space actually, defined by pk equal to pk contains all those points of the real numbers, and it's having the k tuple of real numbers. So pk is defined by this set. This is the set pk. It represents the parametric space. So the point tilde theta is equal to the k tuple is called a parametric point. So any point belong to the space is called the parametric point. So a statistical hypothesis H may be regarded as a statement described by H such that tilde theta belongs to A. So your hypothesis can be in a mathematical form. You can write like this, where tilde theta is the k tuple, it's have k tuple of real numbers, and it represents the parametric point in the parametric space, where A is a specified subset of the parametric space pk. So A is a specified subset of the parametric space pk. Okay, so this is the statement can be written as H such that tilde theta belongs to A. Now I will define simple hypothesis and composite hypothesis. Actually, simple hypothesis is, it's a name of the hypothesis, a hypothesis which specifies the population completely. So let theta 1, theta 2, etc., theta k be the unknown parameters of a univariate population. A hypothesis of the form h naught theta j equal to theta naught j. Theta naught j are given numbers actually. This is your given numbers. Theta j equal to 1 to n is called a simple hypothesis. That means theta j is specified, and the value of theta j is theta naught j. That is, a hypothesis which prescribes exactly of all the parameters is called a simple hypothesis. There is no unknown. You know all the parameters for j equal to 1 to n. Then that type of hypothesis is called simple hypothesis. Okay. Otherwise, the hypothesis is called composite hypothesis. So a hypothesis which doesn't specify the population completely is called a composite hypothesis. Like, if I give you an example of a hypothesis, suppose m equal to 1, sigma equal to 1, h1. So this is, you see, mean and standard deviation both are specified. This is called simple hypothesis. But if I write h2, m1, m greater than 1 and sigma is 1, then sigma is specified but m is not specified. So this is called composite hypothesis. Okay, so that is the difference between simple and composite hypothesis. Next, I will define null hypothesis. And maybe the question is, what is, test of hypothesis I will later define. So test of hypothesis, actually a test of hypothesis is a procedure which specifies a set of rules for decision whether to accept or reject the hypothesis under consideration. Those are called test of hypothesis. I will define once again about the test of hypothesis. Null hypothesis. Next one is null hypothesis. What is null hypothesis? A statistical hypothesis which is set up, whose validity is tested for possible rejection on the basis of sample observations is called a null hypothesis. So a statistical hypothesis which is set up, whose validity is tested for a possible rejection on the basis of sample observations, is called a null hypothesis. And what is alternative hypothesis? Actually, alternative hypothesis are statistical hypothesis which differ from null hypothesis. It's called alternative hypothesis. So the alternative hypothesis is not tested, but its acceptance and rejection or rejection depends on the acceptance or rejection of the null hypothesis. If we reject null hypothesis on the basis of some observation, then we'll accept alternative hypothesis. And if we accept null hypothesis on the basis of sample observations, then we'll reject alternative hypothesis. So alternative hypothesis is not tested. Actually, we test the null hypothesis. We test the null hypothesis. Actually, we test this hypothesis, null hypothesis. We do not test the alternative hypothesis. In the general case of test of hypothesis, we shall not consider a single hypothesis H0 such that tilde theta belongs to A1. That is, H0 is a null hypothesis given by tilde theta belongs to A1 against the alternative H1, which is given by theta tilde theta belongs to A2. A1 and A2 are both two disjoint subsets of the parametric space Pk. These are all disjoint subsets. There should not be any common points of the parametric space. So A1, A2 are disjoint subsets. So that is how you have to write the null hypothesis and alternative hypothesis. Next, we'll define a sample hypothesis. Sample space, sorry. For testing a hypothesis, we are to use random samples of fixed size, say n, drawn from the given population. So, then a random sample tilde x, it's a random sample which contains the n tuple, can be looked upon as the coordinate of a point in the n-dimensional space. You can consider it as a point, coordinate of a point in n-dimensional space. Then Rn, n-dimensional space Rn is defined by this set, where set of n tuple of real numbers is called a sample space. And this space, n-dimensional space, is called the sample space, just like we define Pk, parametric space, for the parametric points. And any given number random sample tilde x is called a sample point. So we gave you the concept of Pk. The parametric space contains the k tuple of real numbers, and we gave you the concept of Rn, n-dimensional space, contains n tuple of real numbers. Those are called sample point, and in this case it's called parametric point, right? You see, we define the parametric point here. Yeah. Yeah, parametric point. So next, the most important thing, if you test, what is the test of hypothesis? Already I have mentioned about the test of hypothesis, but let's again mention that a test of hypothesis is a procedure. A test of hypothesis is a procedure which specified a set of rules for decision whether to accept or reject the hypothesis under consideration. So let n tuple of real numbers be a sample of size n, x1, x2, xn, drawn from an univariate population. On the evidence offered by this sample, we shall have to decide whether to accept or reject a null hypothesis, H naught. The mathematical formulation of this evidence is known as a test of the hypothesis H naught. So, a mathematical formulation is called of this evidence is known as test of the hypothesis H naught. So, a test of hypothesis H naught in its general form consists in choosing a region W. W is a subset of the sample space n-dimensional space Rn, such that if the observed position of the sample point tilde x falls in W, then H naught is rejected, although it may be true. Suppose with the sample observations, you have a value for the test statistics, the mathematical formulation, that is the test statistics. And if this value, computed value of this test statistics falls in the W, which is a subset of the sample space Rn in n-dimensional space, then we'll reject the H naught. And if it is belongs to Rn minus W, that is not in the W, then H naught is accepted, although it may be false. It may be false, but you have to accept because of that analysis. The region W is called the critical region, most important thing in statistical hypothesis, or the rejection region. So W is called the critical region or the rejection region, and Rn minus W is called the acceptance region of the test. Okay. Suppose I'm giving you example of that. I'm giving you some sketch about the critical region or rejection region and the acceptance region. Let me give you a sketch of that. Okay. So suppose your test statistics is a standard normal distribution. Suppose x bar minus m naught, m is specified, and sigma by root n. This is the test statistics. So it follows normal distribution, right? So let me draw a standard normal distribution curve. Okay. So suppose this is your, I will explain this part. This is your some u epsilon, some value, and this is your W. Suppose this is your region of W. This is your W. So this is your, if the value, this is your critical region, and this will be your acceptance region. Okay. This is your acceptance region, and this is your rejection or critical. Suppose this value is P naught. Suppose P naught. If P naught lies in this region, falls in this region, then we'll reject the null hypothesis and accept the alternative. That is why this shaded region is called the rejection region or the critical region. And this region, acceptance region, this is called the acceptance region or the only acceptance region. This region is called the critical region. This one, the shaded portion is called critical region, and this is your acceptance region. Okay, so I will give you more idea in the problems. So that is how this is critical region or the rejection region. If the H naught, value of H naught falls in W. If H naught falls in W, value of the test statistics falls in W. Okay. Next, there will be, so you are dealing with some sample observations and you have to do some test. So there will be some error if you do the test. You are not perfect. And if you do some statistical calculations, there must be error. So that is why in hypothesis we have two types of error. Type 1 error and type 2 error. Once again, I want to repeat with the critical region. The set of values of the test statistics which leads to rejection of the null hypothesis is called the critical region. If you want to say in one sentence, the set of values of the test statistics which leads to rejection of the null hypothesis is called the critical region. Now I will explain the type 1 error. What is type 1 error? This is the error committed in rejecting a null hypothesis by the test when it is true. So if you reject a null hypothesis, true null hypothesis, that is called type 1 error. It was true, but by the sample observation you test that it falls in the critical region and you reject the null hypothesis, then that error is called type 1 error. So let W is a subset of the n-dimensional space Rn be the critical region of a test of the null hypothesis. H naught tilde theta belongs to A1. Against the alternative, this is your null hypothesis, and this is H1 tilde theta belongs to A2, where A1, A2 are disjoint subsets of the parametric space Pk. And tilde theta is the point. K tuple is a parametric point of the space. If the null hypothesis H naught is true, but the sample, random sample belongs to W, tilde x, that is the sample point, belongs to W. So we have to reject H naught, but H naught was true. So suppose if this is, again, if I draw the diagram, normal distribution, standard normal, this is suppose both sides you have a W. This is suppose minus U epsilon and this is U epsilon, right? So you have both tail test. So this both of this constitute W, and this portion is your Rn minus W. Your H naught is true, but the value of the test statistics falls in this region. Suppose that value is Z naught. Z naught falls in this region. So you have to reject null hypothesis because this shaded region is the rejection region or critical region. Or critical. So this type of error is called type 1 error. This type of error is called type 1 error. Okay, because the value of the test statistics falls in the critical region, but H naught is true. This type of error is called type 1 error. And the probability in this case is denoted by alpha equal to probability of tilde bold x belongs to W such that tilde theta belongs to A1, where bold x is x1, x2, xn is the n-dimensional random variable corresponding to tilde x, the sample point of n-dimension space. This probability is called the size of type 1 error. This is called the alpha is called the size of the type 1 error. Now What will be your type 2 error? A false null hypothesis is accepted. So this is the error committed in accepting a null hypothesis by the test when it is false. When it is false, the null hypothesis was false, but you are accepting the null hypothesis by the test. So this type of error is called type 2 error. If the null hypothesis is false, but the random samples tilde x doesn't belongs to W, when H naught is accepted, but it should be rejected, right? So this type of error is known as type 2 error. This is type 1 error and this is type 2 error. And in this case, the probability of committing type 2 error is denoted by probability of accepting H naught when it is false. It is expressed as beta. Beta equal to probability of tilde bold x belongs to W bar, complement of W, such that tilde theta belongs to A2, where W bar is nothing but your Rn minus W. So this probability is called, beta is called size of type 2 error. So very, very important in testing of hypothesis about the type 1 error and the type 2 error. Actually, there are two types of error. Now this error can be represented by this. This is very famous table. So this is explained your two types of error actually. H naught is true. We reject H naught. So this error is type 1 error, right? We should have failed to reject H naught. That should be a correct decision. Which H naught is false and H naught is accepted. This is called type 2 error. Okay. So this is very famous table for you, for your understanding. Now what is the power of a test? Next I will explain what is the power of a test. Power of a test is 1 minus probability of type 2 error. Power of a test is 1 minus probability of, that is 1 minus beta. So probability of rejecting a false null hypothesis, that will be the power of a test. That is defined to be the power of a test. Probability of rejecting a false null hypothesis. Okay. Now, I will explain most things. What is the best critical region now? Number one, there are two things to explain in this best critical region. First, we fix the probability of committing the type 1 error arbitrarily. That is, given any number epsilon, it's a very small number, 0 to 1, in advance, we set probability of bold tilde x belongs to W bar, where W bar is, it's a complementary part of W, that is n dimension space minus W. The number equal to epsilon. The number epsilon is called the significance level of the test. You have to choose epsilon. So epsilon is called the significance level of the test. The equation P bold tilde x belongs to W bar such that tilde theta belongs to A1 equal to epsilon, in general gives rise to a family of critical regions at the significance level epsilon. It gives rise to a family of critical regions at the significance level epsilon. Number two, now in the above family of critical region, we choose, if possible, the particular critical region which would minimize the probability of committing type 2 error. That is, so what is your target? Your target is to minimizing the probability of committing type 2 error, and that is the power of the test. So that is maximizing the power of the test. If I minimize the probability of type 2 error, that means I want to maximize the power of the test, because you see, power of the test is 1 minus probability of type 2 error. So you have to minimize the probability of type 2 error to increase the power of test. This critical region, if existent, will be called the best critical region. So that may be the question. How will you find the best critical region, or what is the theoretical concept of the best critical region? So you have to explain these 2 points. And the corresponding test on the basis of which you are getting this best critical region is called the best test, or the most powerful test at the given significance level sigma. Okay, it is called the best test or the most powerful test at the given significance level sigma epsilon. So that is, these explanations are very, very important. Type 1 error, type 2 error, power of a test, maybe some theoretical questions are there from this part, and the what is the best critical region. Now, oh, this is already explained to you. So now I will explain some important things. How will you choose the level of significance actually? So a computed value of the test statistics will explain a lot of statistics here. State statistic, how will you test if m is known, sigma is unknown? I will explain. So number one, a computed value of state statistics is called highly significant if it falls inside the critical region of the 1% level. 0.01. In this case, we can confidently reject the null hypothesis. So this, in this critical region, you can take u epsilon. So epsilon can be chosen as 1%, so 0.01. If it falls in this critical region, then you can confidently reject the null hypothesis. And this, in this case, the test is called highly critical region of the 1% is called highly significant. Number two, significant. If it falls inside the critical region of the 5% level, but outside that of 1% level. So it lies between 5%, 1% and 5%. In this case, we have some reasons for rejecting the null hypothesis. And number three, not significant if it falls outside the critical region of the 5% level. Not significant if it falls outside the critical region of the 5% level. Okay, so these 3 points are very, very important. Now I will explain Newman-Pearson theorem. That the proof is not required, but this theorem may be important for you. The best, it's on based on the best critical region. The best critical region for testing a simple hypothesis h naught tilde theta equal to tilde theta naught against a sample alternative tilde theta equal to tilde theta 1 is the set W of all points tilde x in the sample space Rn, satisfying the inequality. L is a function of tilde x and tilde theta naught, and the denominator is a function of tilde x, that is the sample point of the n-dimension space, tilde theta 1, sample point of the parametric space. This ratio would be less than k1, where k1 is a constant, L is the likelihood functions. Here, L is the likelihood functions. And where k1 is a constant to be determined as a function of the given significance level epsilon by probability of tilde x belongs to W such that tilde theta belongs to tilde theta naught equal to epsilon by this probability. And tilde theta is a point, sample point, k tuple of real numbers. Tilde theta naught is a sample point, it's not sample point, it's a parametric point, sorry. And theta 1, tilde theta 1 is also parametric point. Theta j are the unknown parameters of the given population, right, are given real numbers. This is already explained. And L is a likelihood function under null hypothesis H0 and alternative hypothesis H1. The next one is under alternative hypothesis. And bold x1, x tilde x is a n tuple of random variables x1, x2, xn corresponding to sample point. So this is Newman-Pearson theorem. This ratio would be less than k1 and this constant k1 to be determined as a function of the given significance level epsilon by this probability. So this is your Neyman-Pearson theorem. So this is about your testing of hypothesis, some theoretical point of view. What is testing of hypothesis? Different types of hypothesis, null hypothesis, alternative hypothesis. What is test statistics? Critical region, best critical region, type 1 error, type 2 error, and power of a test. So, and the theorem. Now I will explain some application to normal M sigma population. Because in the next lecture I will explain the problems, how to deal with the problems of normal, how to do the problems of test statistical hypothesis. So test for first test, let us have application to normal M sigma population. Test for M when sigma is known. When sigma is known, okay. So let's have a, or sample is large. Sample may be large or sigma is known. So let us have a test. So for testing this type of problems, your test statistics is null hypothesis is H0, M equal to M0. M0 is M is specified, mean is specified. Against the alternative H1, M greater than M0. The required statistics is U equal to, this is the required statistics, U equal to X bar, it's a sample mean, minus M0 specified mean, sigma is the sample standard deviation, sigma by root n, n is the number of observations. And you know this statistics we have learned in sampling distribution also. And the best critical region is the interval u epsilon comma infinity, where u epsilon is given by probability of u greater than u epsilon equal to epsilon, where u is a standard normal variate. In this case, your critical region is the right tail of the standard normal density curve. And as such, we say that we are concerned with a right tail test. So let me draw the diagram, standard normal distribution curve. Okay. And this is your u epsilon in this case. And this is your critical region. This is your critical region, the shaded portion. This is the best critical region, that is u epsilon to infinity. If the value of this test statistics, that is u equal to x bar minus m0 by sigma by root n, this value suppose u0. If u0 more than u epsilon, it will fall inside the critical region. If it falls in the critical region, we will reject the null hypothesis. And if you take epsilon is equal to 0.01, that is at 1% level. If you choose epsilon is equal to 0.01, that is at 1% level of significance, then you can confidently reject the null hypothesis, because critical region is the rejection region. Otherwise, if it falls inside the acceptance, not in the critical region, then you have to accept this null hypothesis. This is actually acceptance regions. This dotted portion is the acceptance region. The shaded portion is the critical region. And in this case, we have m greater than m naught. So we have to take the right tail test. Okay. Next. So for testing the null hypothesis m equal to m naught against the alternative m less than m naught, the same statistics, test statistics is same, and the best critical region is given by minus infinity to minus u epsilon. Let me draw the diagram once again for you. Okay. This is the standard normal curve, and this is your minus u epsilon. So this is your shaded portion. This is your critical region. In this case, you have to take left tail test. This is called left tail test because your left portion is your critical region. And this dotted portion, let me dot it with red dots. This is called the acceptance region. So your value of the test statistics falls in this critical region, that is less than minus u epsilon. Then you can reject at 1% level or at 5% level. You have some, if at 5% level, you have some reason to reject the null hypothesis. And if it falls in the critical region at 1% level, 0.01, epsilon is 0.01, then you can confidently reject the null hypothesis. Otherwise, you have to accept the null hypothesis. So this is the test statistics and this is the critical region. And your probability of u less than minus u epsilon, or by probability u greater than u epsilon, because this is symmetric about origin. U is a standard normal variant. In this case, you have to do the left tail test because the critical region is the left tail of the standard normal density curve. Next, if the null hypothesis m equal to m naught against no specific alternative, that is the alternative m not equal to m naught, the required statistic is the same statistics I am using if sigma is unknown, sigma is known. So, and the standard normal curve once again, and you have both sides. So this is called both tail test, and both sides you have critical regions. Okay, you have a both side critical region. So it gives a critical region consists of pair of intervals minus infinity to minus u epsilon and u epsilon to infinity, where u epsilon is given by probability of, if this is epsilon by 2, this is epsilon by 2. So this side will be 1 minus epsilon by 2. This acceptance region will be epsilon by 2, right? So probability of u greater than epsilon by 2, u epsilon is epsilon by 2, where u is a standard normal variant. So you have both side pair of critical regions. So I gave you the concept of right tail test, left tail test, and if there is no specific alternative, you have to go for both tail test. So you have pair of intervals as a critical region. Next, what will happen for test for sigma? So the null hypothesis is sigma equal to sigma naught against the alternative sigma more than sigma naught. The required statistic is a chi-square distribution, chi-square test. So the statistic is the chi-square test, and it's given by chi-square equal to n s square sample variance sigma naught square. And the best critical region is the interval chi square epsilon comma infinity. So it is the same concept is same, where chi square epsilon is given by probability of chi square greater than chi square epsilon equal to epsilon, where chi square has a chi square distribution with nu equal to n minus 1 degrees of freedom. And you will get all the values from the table. You have a standard normal distribution table. You have a chi-square distribution table. Already I have talked about these things in different distributions in separate lectures. So let's draw the chi-square distribution table, curve, density curve. So this is your chi-square distribution curve. This is not symmetric. So this is your chi-square epsilon, suppose. And this will be the critical region in this case. This is the critical region. And in this case, you have to do right tail test again. So this is called right tail chi-square test. Okay. And where chi-square is a chi-square distribution with n minus 1 degrees of freedom. Similarly, we can explain the left tail test and the both tail test also for chi-square. Okay, let me show you in one diagram. So you have a chi-square distribution table curve. Sorry. Okay. This type of curve. So you have, suppose this is your chi-square epsilon, and this side you have chi-square minus epsilon. So you might have both side test, okay, and left tail test also. So this chi-square distribution is chi-square with n minus degrees of freedom. Now next, test for m when sigma is unknown. You have to remember all these statistics actually. Only these statistics. You have chi-square statistic, chi-square distribution, t distribution, standard normal distribution, and sigma is unknown or sample, small sample. Sample may be small. If a sample size is less than 30, that is called small sample. If it is more than 30, approximately, that is called large sample. So you have a alternative hypothesis. Your null hypothesis is m equal to n m naught. Alternative is m more than m naught. So the required statistics is t statistics, t distribution, that is x bar minus m naught by small s by root n, where the critical region is t epsilon comma infinity. Okay, and this is the, it's much steeper actually, t distribution curve. Yeah, this is the t distribution curve once again, and this can be t epsilon, and this is your critical region. The same explanation, where t has a t distribution with n minus 1 degrees of freedom, and in this case you have right tail test. If m less than m naught, you have a left tail test. If there is no specific alternative, you have both side test, both tail test. Okay, so it is same for the standard normal curve, same standard normal distribution. You have a left tail, right tail, both tail. Okay, now I will compare two normal populations. So suppose you have two normal populations having parameters m1 sigma 1 and m2 sigma 2. Then, and in this case, sigma 1 and sigma 2 are known, and they are given by equal to sigma. Both are known, and they suppose they are equal, and that is equal given by sigma, or sample is very large. Then you have to test m1 equal to m2 against the alternative m1 more than m2. The required statistics is u equal to x1 bar minus x2 bar. If sigma 1 sigma 2 are different, then you have this formula. If sigma 1 equal to sigma 2 equal to sigma, then this result comes into this. This is your test statistics, where x1 bar, x2 bar is the sample mean, sigma 1 sigma 2 is the sample standard deviation, n1 n2 is the sample size of the first, normal distribution, and n2 is the sample size of the second normal distribution. So this is the state statistics. And the best critical region is u epsilon comma infinity. So you have a right tail test of the standard normal curve. And m1 less than m2, if your alternative is m1 less than m2, you have a left tail test. And your best critical region will be on the left hand side. And if there is no specific alternative, then you have to test for h1. Alternative will be m1 not equal to m2. So you have to go for both tail test. Okay, clear? So you have to remember this state statistics. Next, if sigma 1, sigma 2 is unknown, equal to sigma, suppose, standard deviation same, but they are unknown, then what will be the test? The test will be T statistics. The statistics will be, test statistics will be T, where T equal to root over n1 n2 over n1 plus n2 times x1 bar minus x2 bar by n1 s1 square minus n2 s2 square, where nu is n1 plus n2 minus 2. Nu is the n1 plus n2 minus 2, because T has a n1 minus 1 degrees of freedom. T distribution, T follows T distribution with n1 minus 1 degrees of freedom. And another one mean T follows n2 minus 1 degrees of freedom. So combined will be nu n1 plus n2 minus 2 degrees of freedom. And you can get the value from the T distribution table. So in this case, you have right tail test, T distribution right tail test, and m1 less than m2. If sigma is unknown, you have a left tail test. And if there is no specific alternative, you have both side test. So you have left tail, you have right tail, as already explained. Just you have a new test statistics here if sigma is unknown. Now you have test of equality of variances. This is very difficult one. So sigma 1 equal to sigma 2 is the null hypothesis. Alternative will be sigma 1 more than sigma 2. And if your required statistic is the F statistics, S1 square by S2 square. And you know that S1 square is given by, small s1 square is given by n1 by n1 minus 1 capital S1 square, right? Sample variance. So, and S2 square is similarly. So this is your test statistics. This follows F distribution, and you know that what is your F distribution, and you know the region for F distribution also. F epsilon is given by, F has a F distribution with parameters nu1 equal to n1 minus 1 degrees of freedom, nu2 equal to n2 minus 1 degrees of freedom. Okay. Next, we have binomial NP population. So let the parameter n be known and large, and let nu be an observed value of the binomial NP variate x, that is a sample of size n from the binomial population. Then you have to test the null hypothesis P equal to P naught. The required statistics is U equal to nu minus NP naught by root over NP naught Q naught. You know that mean of the binomial distribution is NP and variance is, standard deviation is NPQ, root over NPQ. So you have this statistics, U equal to nu minus, and nu be an observed value of the binomial NP variate. It is an observed value. And the critical region will be pair of intervals. You have a pair of intervals where U is a standard normal distribution curve. So you have a pair of intervals, U epsilon and minus U epsilon, right? You have a pair of intervals like this. Okay. So you have a pair of intervals, and that is U epsilon is given by probability of U greater than U epsilon equal to epsilon by 2, where U is a standard normal curve. So in this case, you have pair of intervals. You have to remember this for, and this is the state statistics for binomial NP population. Now comparison of binomial NP population. What is the comparison? So if there are two binomial populations, N1 P1, N2 P2, and nu1 nu2 be the independent samples of unit size, then your test statistics is given by u equal to nu1 by n1 minus nu2 by n2 root over p cap q cap times 1 by n1 plus 1 by n2. This should be n2. Sorry, there is a typographical error. And p cap is given by nu1 plus nu2 by n1 plus n2, and q cap is 1 minus p cap. And the critical region consists of the, again you have a always in binomial you have a pair of intervals, that is you have both side test and u is a standard normal variant. So you have pair of best critical regions on the left and on the right also. Poisson mu population. Next. So suppose X is a Poisson mu variant and the null hypothesis is mu equal to mu naught. The required statistics can be taken as u equal to nu minus mu naught by root over mu naught by n. And in this case also you have a pair of best critical regions on the left and as well as on the right also. Okay. This is your Poisson mu population. And lastly, we have discussed multinomial population. This is the last one in my lecture today, but there are more. Chi-square, goodness of fit, and chi-square, all this maybe I will discuss in the lecture problems. If I discuss with the problems, I will discuss that portion. Let xk be a binomial npk variate. So there are multinomial. So there are k equal to 1 to m. There are many binomial populations. Let nu k be a sample of unit size from the population of xk. And for testing h naught pk equal to p naught k. P naught k is the given observed value. And summation p naught k equal to 1. And n is large. The required statistics is chi-square actually. Chi-square. You have a chi-square distribution. And in this case, you have right tail test. You have to take right tail test. Nu k minus np naught k whole square by np naught k. P naught k is the given positive numbers. N is the size. Okay, n is large. So this will give you the chi-square distribution. So these are all test statistics I have explained, and how to test if it is a right tail, if it is a left tail, if it is a both tail. So we have discussed far about some applications. Test for m if sigma is known. Test for sigma if test for sigma, and also that is for chi-square distribution. Test for m when sigma is unknown, that is t distribution. Test for equality of means, it's a standard normal. Test for equality of means when sigma is unknown. Test for equality of variances, that is f distribution. Test for binomial distribution. Test for equality of binomial distribution. Test for Poisson, and test multinomial. So this is a large list of hypotheses. So I think in this lecture we have covered. This is a long lecture, I guess. Thank you for your patience, all of you. So the testing of hypothesis, the very difficult chapter of statistics, I think I tried to clear all these doubts and your clear concept about the test of hypothesis. So follow my lecture video. I will post very soon the problems dealing with testing of hypothesis. Thank you, all of you.